chapter 1.8 about continuity, discontinuity. So there's three conditions in which we can define a function is continuous or discontinuous at an x value. Okay, so here's the kind of definition and our three conditions. So the definition is for a function to be continuous at a single point. That y value at that point has to exist. So that's condition number one. So f of a has to exist, meaning that a is in the domain of the function. Okay, so it has to exist. And then two, the limit at that value also has to exist, and as well as the third condition, that limit has to be the same as when you plug in that x value into your equation. Okay, so what this means basically, if you are drawing your function, you can't pick up your pen. I mean, that's what definition kind of continuous is. So that means that when I draw my function, I just can't pick up my pen, and it can go however it wants. There's some conditions within that as well, but for kind of all, just regular looking at it, that's kind of the case, right? It has to be continuous. So at some x value, I have to have, so I can't have an open circle here. Okay, so I can't have an open circle. So anytime I have an open circle, right, that means that f of a is not in there. It doesn't exist, right? So that means a is not in my domain. So that fails condition number one. Okay, or f of a could be in my domain because it could be defined maybe right here. Well, that means this fails condition number three because my limit, the limit exists, but the limit is this y value right up here, right? But my f of a, it's that value, so that would fail on condition number three. So you can't have any holes with a point somewhere else. And definitely you can't have if I would come to two different values. So if my function went like this, like that, that means the limit doesn't exist, right? Because from the left, the limit's up here. From the right, the limit's down here. So the limit doesn't exist. So you can't have any holes. So you can't have holes. You can't have holes that have some kind of dot somewhere else, and you can't have go into two different places. So you can't have those. Those would be the three conditions for a function to be continuous. But in all practical reasons, it would just be you can't just pick up your pen. So anytime I had a circle, I had to pick up my pen and make a circle. So it's not going to be, or down here I had to pick up my pen. So it's not going to be here. I had to pick up my pen and put a point. Oops. So that's not going to work. And the final one, I had to pick up my pen. Pick up my pen in order to draw that second part of the graph. So in all intents and purposes, as long as if you pick up your pen, then it's not continuous. All right, so here's some few examples. Here, if I plug in 2, I'd get 0 on bottom, right? And I can't divide by 0, so that means that 2 is not my domain. So f of 2 is not defined. So that means by condition 1, it's not going to be continuous. Never spelled continuous. It's not continuous, at least at that point. On the other part of the function is, but not at that point. Here's another example. So we have a piecewise function. So as long as x is not 0, right? So this example might look something where you have two different equations. If x is 0, then you have 1. So if x is 0, then you have this point, and then all else follows this, right? So it might look something maybe like this, like that. So it's not at 0 if I plug it in. If I plug in a 0 here, right, I'd get undefined. But I am defining, so f of 0 is defined. So it meets condition number 1. But the limit here, as this continues to go up from the left, it goes up to positive infinity, and from the right it goes up to positive infinity. So the limit kind of exists, right? So the limit exists because it both goes up to positive infinity, but f of 0 equals 1, where the limit does not. The limit does not. It equals this, so it's not the same. So really, this is actually by condition number 2, because when the limit exists and it goes to infinity, technically the limit doesn't really exist because it goes on to infinity. And then, but also these two are not true as well, right? So this one actually fails. Fails condition 2 first, and then it also contains condition 3. So here's another example. So now here we go. Here we got a piecewise function again. So here, if I plug in 2 here, I get 0, so that's not going to work. But that's why I have a piecewise function, so I can plug in 2. So here at 2, 1, 2, I am defined again at 1. Right? But then, as I look at this top equation, well, here, f of 2 equals 1. So that's good, it's defined and equals 1. But the limit, as we look at this one, right, I can simplify, I could factor that x minus 2, x plus 1, and the bottom's x minus 2, right? So those x minus 2 is going to factor, so I can go ahead and plug in 2, right? And plug in 2, so I get 3. So the limit equals 3. Limit, we'll just say f of x equals 3 as we go towards 2. But f of 2 equals 1. So because these are not the same, by condition 3, it doesn't work. Or, sorry, not continuous. Okay, so the types of discontinuity kind of already talked about a little bit with the different graphs. We have a hole, right, and then it continues on. So this is not discontinuous. This is by condition 1. So we have a hole. Another one, we can fill that hole. So here continues, but then we define it here. So that meets condition number 1. But in our limit here is say 2, and this is 1. Here this would fail condition 3 because f of whatever a this is not the same as the limit. So that would be condition 3. Condition 2 is where f of a is defined. So it might be defined at some point, but the limits are not the same. So here the limit does not exist, right? Because it's going to 2 different points. But our f of a is defined right there, so it meets condition number 1, but fails condition number 3. And if it fails condition number 2, then it might fail condition number 3. But this is condition number 2. So this fails condition number 2 because the limit doesn't exist. Does not exist. So it fails 2. So there we have, this is called a jump. I have a jump there. These are holes, movable holes. And then we also have vertical asymptotes, so that's kind of our last one, which we saw in that one problem. Right, so here's a vertical asymptote. Okay, so here's some types of functions that are continuous in their domain. Polynomials are always continuous on their domain. Rational functions are continuous on their domain. All right, so that's ones we looked at divided by x minus 2. Right, as long as we don't use 2, then we're good. Then it's continuous all but at 2. Square roots are, right? Can't go negative square root. All trig functions are continuous on their domain as well. Okay, we'll talk about a couple things here. Continuous composite functions. So if we're looking at the limit as x goes to some a of a function inside a function, then we can just take the limit of the inside function evaluated at the outside function. So we find this limit of g of x and plug that answer into our function f, and that will give us the limit of the composite function. So for example, if I want to take the limit as x goes to 0 of sine of x squared, well, then I can just take the limit as x goes to 0 of x squared and then plug that inside of sine. So then I just go plug in 0 into that, so I get 0, and now I take the sine of 0, and that is 1. So the limit of this as x goes to 0 is 1. So the last thing we'll talk about is the intermediate value theorem. So as we're looking at a function and say that function is on a closed interval, so from a to b, and there's some value n where n is between f of b, so that'd be plugging in b into your function, see what you get, and between f of a, plugging in a into your function and see what you get. Then that means that there exists some value c between a and b such that f of n would equal that. Such that f of c, that's a beautiful f of c equals n. So if you have some interval from a to b, and then you get those y values that are also between that. My graph didn't do precise with that. Let me fix it. Okay, so we have f of a is right here, f of b is right here. So there has to exist some c value that n would equal that. So as long as I have some function and it's a continuous function, so it has to be continuous on that interval from a to b, then there's some value between a and b that gets you a value of your y between these two y values. Basically, that's what it says.